Good afternoon, everyone, and thank you for sticking around. I'm the last, so if I'm standing between you and that Friday pint, thank you for being here. Um, my name is Andrey. I'm a postdoc at Oxford. My work has been mainly funded by the Faraday Institution, to whom I'm very grateful. And I'm also grateful to a lot of collaborators. Rob Green at University of Saskatchewan, Canada, Rob Weatherup and group at Oxford, Rob House, also at Oxford, and my co-supervisors, Ben Morgan and Saiful Islam. I will talk about a battery cathode. In particular, if you open up a high-end car, you will see a lot of layered nickel-based materials in its battery electric car. You will see a lot of nickel-based layered oxides as its cathodes, and that's what this is about. Um, in particular, I will talk about lithium nickel oxide, which is kind of the end member of all the practical ones. The practical ones have usually a little bit of cobalt and a little bit of manganese. But this is the prototype system, if you will, that maxes out all the distinguishing characteristics of these systems, of all these layered cathodes. And plus, it only has one transition metal, so it's a little simpler to model. On the right is this very atomic picture, these gray octahedra with gray nickels in the middle make a layer, and then these green octahedra with green lithium in the middle make up a lithium layer. And as the battery is charged and discharged, the lithium goes out on charge and lithium comes back in on discharge. It is a astoundingly odd material. The first time it has been synthesized was about 70 years ago. The first time it was put into a battery was about 30 years ago. And I contend it's only now that we properly understand what it's doing. But the reason it's worth the time is because of all traditional battery cathodes like lithium cobalt oxide, lithium manganese oxide, and mixtures of the three, it has the highest capacity for a given voltage. And nickel is not super great in terms of abundance, but it's a lot better than cobalt. So this is worth studying. And certainly a lot of industry has moved in the last few years from cobalt-containing compositions to cobalt-free compositions that are becoming majority nickel-based. However, it is considered that nickel is responsible for surface degradation. Nickel is responsible for worse thermal stability of lithium nickel oxide compared to lithium cobalt oxide, for example, and high voltage stability. So typically you can take these to about 4.2 volts in a battery, but above 4.5 or 4.6, they're quite bad. They will degrade and they will not survive. So today, I want to touch on a few unexplained physics observations, real experimental observations of this material. I'll propose a model for why these things happen. And we will test. I'll show you how we test to verify this model that starts out at the level of density functional theory introduced by Professor Staunton before me. We will verify these models with experimental observations with synchrotron X-ray spectroscopy. And a little bit of bonus coming back to the actual batteries at the very end. So we'll start with this sort of inorganic chemistry picture, going to considering a transition metal that has d electrons. And in particular, nickel has, formally speaking, on average, 7 of those. And that means in its octahedral environment, it either wants to distort, make a couple of those bonds longer. That will make this purple set of orbitals here. We'll call it a Jahn-Teller distortion. Or one nickel can find a partner and they can share those electrons unequally. And so that will take what would have been a formally 3+ nickel in purple to a pink one, which would be formally 4+, and a green one, which would be formally 2+. So one of them, it's going to do some combination of these two things, either a distortion and stay 3 plus, spin half, one unpaired electron, or a disproportionation into something that is formally 4 plus, no unpaired electrons, spin 0, and something that is spin 1, two unpaired electrons, formally 2 plus. A lot of inorganic chemistry and nomenclature here, but I'll keep the colors. You should be able to understand the rest of the talk with just the color coding. So we know also that the sodium nickel oxide compound, where the nickel oxygen layers are the same and the lithium is replaced by the sodium, only exclusively does this purple thing. It's exclusively 3 plus and very distorted. We can see this in the crystal structure. And I'm going to contend that lithium nickel oxide does a very weird mixture of these three things. And that bears on its battery properties as well. So two things that previously had not been really explained is, for one, electronic conductivity. A battery cathode does need some electronic conductivity, and this electronic conductivity of lithium nickel oxide is a lot larger than that of sodium nickel oxide, the orange relative to purple, but a lot less than that of silver nickel oxide. Same structure, but silver nickel oxide is metallic. And the second one is the evolution of the average magnetic moment as the lithium is taken out of the cathode upon charging. So there's this curve would describe a nickel 3, nickel 4 redox. This would be the normal expectation. And in particular, when this material is pristine at the far right of this plot, its magnetic moment is too high to be all nickel 3 plus. And by the end of the talk, I hope we can I hope we can explain this. But starting with atoms, there are some dynamics. So here is a prior study by a very competent German group who simulated this material at the density functional theory level, and they found that these distortions of these bonds are moving around and switching around very, very rapidly. So they are plotting here the average bond lengths of this nickel oxygen octahedron, and the x-axis is in femtoseconds. So they're covering a couple trillionths of a second. And they're showing there's always a long bond and there's always some short bonds. So we will try this as well, but we will track the magnetic moments because that separates our nickel 2 from 3 from 4 plus. And this is what we see. Also, this also covers an extremely short amount of time, still about a trillionth of a second. But what's plotted there are the magnetic moments. So at the bottom near 0 is our nickel 4 plus. In the middle is about nickel 3 plus, and at the very top is spin 1 nickel 2 plus. And what we so it's kind of, again, these are our color-coded octahedra. What we see in this simulation is that this process of disproportionation and distortion can be dynamic. And so very rapidly, two of these spin half ones that are 3 plus each can become 2 plus and 4 plus, and back, and disproportionate and come proportionate. The other thing we see is that they can switch their spins. And that would be quite similar to something like a very localized electron moving about between these nickels. So this process on the left, we would call it an exchange, would correspond to, for example, the motion of charge. And if we track this, then maybe we can say something about the conductivity that was previously not very well understood. But this is a very small chunk of material, so only about 100 atoms for about a trillionth of a second. How do we get from this to something testable? How do we know if this is even true? Right now is just wave functions in a computer. So we can do what's more or less a glorified histogram. So on the x-axis here is the magnetic moment. It was on the y-axis on the previous slide. And on the y-axis is just size. We find that these spin 1, 2 plus octahedra are a little bigger, the ones in green. Dark is lower energy. And lower energy here means more or less just higher probability. And we can then do this as at a few different temperatures. And now we're getting towards an experimentally testable prediction. There are 3 free energy basins, but they don't stay constant in temperature. So at low temperatures, these 3 different possible states of nickel are roughly equal in probability. But as temperature goes on, one of them, this like purple spin half one, formerly 3 plus, becomes predominantly becomes predominant, becomes the most the solo low energy basin. This is testable. We just need a probe that can distinguish these states. And then the transition between these is a saddle point, a high point in free energy. And oddly enough, the energy of this point corresponds to about half that of the activation of conductivity. So this process of exchange can, in fact, plausibly be the conduction of electrons in this material. One more aside is how do we test this? Kind of experimentally, we can do some form of X-ray characterization and X-ray absorption fine structure that can give us a distribution of bond lengths or neutron diffraction or kind of various similar tools. But in the computer, we can generate theory at a variety of different levels. And sometimes we can have different levels of theory, both density functional theory, but slightly different flavors of it, give us a distribution of bond lengths that is basically indistinguishable and more or less consistent with experiment. However, these different flavors of theory can give us drastically different predictions of the electronic structure of the material. Here on the right, the one in pink happens to predict a much higher prevalence, in fact, an order of magnitude higher prevalence for these disproportionated 2 plus and 4 plus states. So we need an experimental probe to verify whether this is true that can distinguish 2 plus from 3 plus from 4 plus. And so for that, we turn to 3 different flavors of X-ray spectroscopies. Oh, yes. So one aside is that when we say X-ray absorption, it's not really exactly absorption. We excite with X-rays a transition from nickel 2p to these valence and conduction orbitals that are hybridized nickel 3d and oxygen 2p. We can measure what's called partial fluorescence yield. So we measure the photon that comes back out. We can also put a sample in a very strong magnetic field and measure the difference between 2 polarizations of X-rays being absorbed. It's called circular dichroism. Or we can add a second dimension to the X-rays out that we measure, and that is inelastic scattering. So we have a very fancy spectrometer. And so, okay, we have a model for the states of nickel. We have some ways to test what's correct. But now we need to actually not only predict the states of nickel, but predict their spectra in these spectroscopies. So we turned into the semi-empirical level of what's called multiplets. These take crystal field theory and ligand field theory to identify symmetry distinct states for the valence and frontier 3D orbitals. And these are the orbitals into which the X-ray excitation goes. We then combine, and so this theory can predict for us these absorption lines in X-ray absorption spectra. Then we then more or less make a reasonable assumption about how wide they are. So on the right is a very model example of nickel oxide spectrum. at the nickel L edge. So it's an excitation from nickel 2p to nickel oxygen 3d 2p orbitals. We'll skip the Harrison formulas for time. That's another set of parameters that is important in following for doing this credibly. And so we are slowly getting towards experimental verification here. We predict that the 3 different states of nickel that we have in our DFT simulation will in fact have different hybridization between the nickel and the oxygens in the valence band. And that can be reflected in part in the different bond lengths, different sizes of these local octahedra. And it can also be reflected in where these electronic states lie next to the valence band edge. So here we have these 3 different blobs, which would be electronic states that are distinct for each of the 3 different nickel species. Again, this is very atomistic, so bear with me. We will get to batteries in the end. This dotted horizontal line is the boundary between lower energy states that are full of electrons and higher energy states that are empty. We can only excite into the empty states. And we see that the 3 different nickels have rather distinct energies for their empty states. So now we can be confident that our spectroscopies can in fact distinguish these 3. Okay, so we have a model to test, and we think we have a method that can in fact test it. So let's see what we do. So on the left is a plot of the partial fluorescence yield spectroscopy at 3 temperatures for lithium nickel oxide and a comparison for sodium nickel oxide. We see that the nickel one, the lithium compound, changes at least a little bit, with the middle of that spectrum growing. And that middle also happens to correspond to how the sodium compound looks in its entirety. And so we can say that ever so slightly, upon heating, the lithium nickel oxide becomes like sodium nickel oxide. The sodium nickel oxide is exclusively spin half, those purple ones in the middle, formerly 3+, but all of them. And so qualitatively, this is consistent with what we predicted. We predicted that this disproportionation in lithium nickel oxide would be favored towards cold, and they would comproportionate back and start looking like sodium nickel oxide when it's heated. And that is what the spectrum is consistent with. We can more properly decompose the entirety of these spectra into these 3 components. And here again, the colors correspond to the same as before. As expected, the sodium nickel oxide is exclusively spin half. And lithium nickel oxide is about a third of these 3 distinct nickel species. But this is only one of 3 spectroscopies, and really people can complain that this is not enough. So we turn to magnetic dichroism. We put the sample in a magnetic field, and that should highlight unpaired electrons specifically. Specifically, this should highlight this spin 1 nickel 2+ component that is there in the lithium compound, and not there in the sodium compound. This is what our spectra look like. And in particular, we can compare them to a exclusively nickel 2 compound. And the key feature to test correspondence is a sign change. And a nickel 2+ should have a sign change, and we do in fact have that in the lithium nickel oxide, but not in the sodium nickel oxide. Overall, pretty good correspondence. And so this tells us that we do in fact have a 2+ in the bulk. We could do similar, but with inelastic scattering for nickel 4+. We can our theory makes a prediction for what that spectrum should look like. We take now a 2-dimensional spectrum, and there are in fact blobs in that absorption spectrum that correspond exclusively to a nickel 4+ state. So to summarize intermediate, we have a model that we think works. Let's test it. So this works at all states of charge of a battery. So on the left is a very surface-sensitive X-ray spectroscopy, but now as this cathode is going from discharged to charged. This also works in, to our knowledge, all the relevant modalities, including a very bulk-sensitive one. So this is again the bulk of cathode particles as the material goes from discharged to charged. And so now, from this spectroscopy that we can now fingerprint, we can conclude what percentage of each of the three nickel species is there at any state of charge of the battery. And so I just think this is kind of fun to do, and I hope this becomes useful to people who do this sort of spectroscopy, because they can take our fingerprints and try their own. This now spectra confirm that in the pristine material towards the left of this plot, there's about a third of three different nickel species. And that is consistent with the conductivity, because we talked about the exchange of spin and kind of charge between distinct nickel species. That I think that corresponds to conduction of electrons, and it's consistent. And it's consistent with the magnetometry, because the 2+ would contribute a little extra magnetic moment to the pristine material. So now we can explain that as well. And finally, to summarize, this looks like very traditional nickel redox, nickel to 2+ to 3+ to 4+ as the battery charges. And we can, from spectra and from computation, where on the left is spectroscopy and on the right is a cluster expansion simulation based on DFT, we can predict the speciation of the transition metals at any state of charge in this nickel-based cathode. Thank you, and I look forward to your questions.